All right. Hello, everyone. So you sent us some fascinating source material, and we've done a bit of a deep dive. And today's topic is, well, it's a really interesting mix: calculus and milk.
Yeah, milk. It sounds a bit unusual, maybe, but it's actually a great example. We're looking at um, how some pretty core mathematical ideas, specifically derivatives, are used.
Used to model the cooling rate of milk, right? Inside an agricultural processing facility.
Exactly, a dairy plant.
It's quite something, isn't it? Bringing that level of mathematical precision to food processing.
It really is. And it's crucial stuff. Milk cooling is vital for safety, for quality.
Hmm.
After pasteurization, you need to get that temperature down fast to stop bacteria growing, keep it fresh.
Okay, so let's unpack this then. The source material points directly at derivatives, calculus territory. You know, the math tool for looking at rates of change. How does that high-level math connect to, well, a big tank of cooling milk?
Well, the key is right there in the phrase cooling rate. That is a rate of change, isn't it? It's literally how quickly the milk's temperature is, changing over a period of time. And a derivative is this specific mathematical tool designed to capture that instantaneous rate of change at any specific moment.
Ah, okay. So it's not just like checking the temp now and then checking it later to get an average speed. The source is saying derivatives let the plant know exactly how fast the temperature is dropping, like right this second.
Precisely.
Yeah.
Yeah, that's the core idea. It allows for a really dynamic understanding, a model of the whole cooling process. Think about it. Just dipping a thermometer in every 15 minutes. That gives you snapshots, isolated points in time.
Right.
But the derivative model, that gives you the continuous movie. It can show if the cooling is suddenly slowing down, or maybe if one batch is cooling way faster than another.
And that's where it gets really practical, I suppose. The source mentioned it often builds on things like Newton's law of cooling.
Yes, exactly. Which brings in real-world factors, things like the temperature difference between the milk and the cooling medium around it, also the volume of the milk, the surface area, and how efficient the cooling system itself is running.
So it's not just abstract math floating about. It's a model that pulls in actual variables from the facility, from that specific batch of milk. How is that useful, like, on the ground?
Well, it answers a big question. How do these plants make sure the cooling is consistent and safe, even when conditions change? Maybe the outside air temperature shifts or a pump isn't quite optimal. Math gives them the framework.
Okay.
A derivative-based model lets operators predict, pretty accurately, how long it should take for the milk to hit its safe target temperature, given the current readings.
So if the ambient temperature in the plant goes up a bit.
Exactly. Or if the cooling system shows signs of maybe reduced efficiency, the model can flag it in real time. It can show, hey, at this rate, you're not going to hit the target temperature on schedule.
And then they can react immediately.
Right. Adjust the system, check for problems, whatever's needed, before it actually becomes a food safety issue. That's the key.
That level of prediction, that real-time insight, I guess that just wasn't possible with the older methods, just checking periodically.
Not really, no. And it also allows for optimization. You can use just enough energy to cool the milk efficiently. You're not wasting power by overcooling, but you're absolutely ensuring speed and safety. It's a balance.
So what this boils down to then is that these theoretical math concepts, derivatives, developed ages ago. They're providing really powerful practical tools for something essential today, like cooling milk safely in a modern factory.
It really highlights how abstract math tools get applied every single day, often in places you wouldn't necessarily expect. Solving complex, practical problems, optimizing things, making sure processes are safe, efficient, high quality.
Okay, so let's sort of wrap this up. The core idea we pulled from the source material, derivatives, give us a precise, dynamic way to model that crucial milk cooling process.
Yep, it's a fantastic example.
And it really underscores how these math tools, especially ones dealing with rates of change, have direct real-world impact in industrial settings, like a dairy plant, affecting vital things like temperature control.
Absolutely.
So thinking about this example, it makes you wonder, doesn't it? Where else might complex mathematical tools be quietly working away, solving problems in industries that seem, relatively simple or unexpected on the surface?
That's a great question to ponder. They're likely hidden in plain sight in more places than we realize.
Definitely something to think about. Thanks for tuning in.